Today we're going to continue on our review chapter of Chapter 2 in dealing with chemistry and talk about some chemistry basics building on what we've talked about already in terms of our atomic structure and our different elements. So if we take atoms of different elements and start combining them, they're going to start to form chemical bonds. And so some atoms are going to be attracted to each other, they're going to have these strong attractions, and when two or more atoms bind or stick together, we call that a molecule. And so as we start thinking about molecules, it's kind of a step up in scale. Atoms are smaller scale, we start combining atoms together into molecules. And so, for example, if we take a sodium atom and a chlorine atom and we mix them together, they will form a chemical bond and a molecule of salt, or sodium chloride. Now, there are many, many types of chemical bonds out there, but there are three common types I want to go over in class that we'll really see that are important for living organisms. And those three types of chemical bonds are ionic bonds, covalent bonds, and hydrogen bonds. And so we're going to go through each of these, talk a little bit about what each type of bond is, and some examples that we might see in living organisms. As the name implies, ionic bonds are going to involve atoms that have electrical charges. They're going to be based on ions. And we know that if we mix atoms together, sometimes one atom will donate or give away an electron to a second atom. And remember, atoms that have a full outer shell of electrons are very stable. And so as these electrons are being exchanged, it's filling up outer shells. Of course, if an atom loses an electron, it's going to have an electrical charge. It's going to have too many pluses. It would be a positive ion. Likewise, that atom that gains an electron now will have one extra minus, so it would be a negative ion. And so as we see this electron being shuffled around, it's going to create these two oppositely charged ions, a positive and a negative. The ionic bond in particular, though, is when that positive ion and negative ion are next to each other, they're going to be very strongly attracted to one another. We know that like charges are going to be attracted. And so that ionic bond technically is that attraction between those oppositely charged ions. And as we mentioned on the last slide, salt is a nice example of that. We know sodium has that one extra electron in its outer shell, so it tends to lose that electron. Likewise, chlorine needs one electron to fill up its outer shell. So when we mix sodium and chlorine together, that electron is transferred from sodium to chlorine. Now both atoms are more stable because they have a full outer shell, and they're also going to be very strongly attracted to one another. And that's going to form our molecule of salt, that strong plus-minus interaction. Now typically we're not going to just see one sodium and one chlorine atom together, but we're going to see many mixed together, and that's going to form salt, which we know forms crystals. And the reason for that is each positive sodium, in this case yellow on that right side of the figure, is going to be surrounded by those green or negative chlorines. And likewise, each negative chlorine will be surrounded by positive sodium ions. Our second bond type that's going to be important in living organisms are covalent bonds. And covalent bonds are going to involve atoms that don't simply give away or take electrons from other atoms, but instead they're going to involve elements that have atoms that tend to share their electrons. And if we look at the periodic table and think about the elements that are involved in sharing, these are elements that tend to have several electrons in their outer shell that are sort of like carbon, that have 4 electrons in its outer shell. So it would either have to gain 4 or lose 4 electrons to have a full outer shell, and we're simply not going to see that because that extra plus minus is really going to throw off the stability of the chemical. And so those types of atoms tend to share their electrons, meaning the electrons are going to orbit not just one atom, but 2 atoms. The electrons are going to take turns orbiting one nucleus and then orbiting back to the next nucleus. And this is a compromise of having a full outer shell sometimes, but without disrupting that plus-minus balance so much. And atoms like carbon, oxygen, nitrogen, some of those that are most common in living organisms, tend to be involved in these sharing or covalent bonds. So not surprisingly, those covalent bonds are extremely common in the chemicals that make up our structure and make up the bulk of us as living organisms. Now, covalent bonds are a little bit more complex than ionic bonds because, as we all remember from the playground as a kid, not everybody shares the same. There was always that kid that didn't play well with others. Well, we're going to see a similar sort of thing here with electrons. That sharing is not always going to be the same. Some atoms are better sharers, some not so good. And so I just want to take a look at some different types of covalent bonds and how we might classify them. One way to classify these covalent bonds is simply by, well, how many electrons are going to be shared? How much is going on between these two atoms? And it's pretty simple. The most common type of covalent bonds are single bonds. One pair of electrons are going to alternate going back and forth between our 2 different atoms. Double bonds are a little less common. That would involve 2 pairs of electrons being shared and working their way back and forth. For example, oxygen or O2 gas is held together by a double bond. Rarely we may see a triple bond in living organisms, 3 pairs of electrons being shared between 2 atoms. But this doesn't happen too often, but on occasion we may come across it. A second way that we may group or classify covalent bonds is how the electrons are being shared. And this was that example I mentioned a couple seconds ago about the kid on the playground not playing well with others. Sometimes sharing is equal and sometimes it's not. If we have a situation where the electrons are shared equally, meaning they spend equal time around each atom, they kind of alternate back and forth from one nucleus to the next, that creates a nonpolar covalent bond. And nonpolar covalent bonds, the important chemical aspect here is that they're going to be electrically neutral. There aren't going to be any electrical charges associated with these bonds. And because that electron is equally spaced, we're not going to see any plus minuses. And you can sure bet that a nonpolar bond with no plus minuses is going to have very different chemical properties than something like salt, which had those strong plus minus ionic bonds in it. Our other option for covalent bonds then is they could be polar covalent bonds. And a polar bond is when we have unequal sharing of electrons, meaning that that electron is going to spend a lot more time around one nucleus and then maybe only occasionally orbit the second nucleus. And so it's going to be very lopsided. Now, because that electron is lopsided in terms of where it's spending its time, the nucleus where the electron spends most of its time is going to have a little bit of a minus charge because those electrons are at that end more often. The other end of that molecule is going to have a little bit of a plus charge because the electron's not there very often. And so polar bonds are going to differ from those nonpolar bonds in the idea that they're going to have very small plus minus charges inside of that chemical. And so chemically they're going to behave differently than those neutral nonpolar bonds. This chart just shows several types of covalent bonds. Here's a single bond on top with hydrogen, that's just one line connecting the two H's, and a single pair of electrons is going to move equally back and forth between those two hydrogen nuclei. There's our oxygen, our double bond holding our O2 gas together. We can see two lines is how we draw that. Methane is carbon with 4 single bonds to hydrogens, and so each of those hydrogens has a pair of electrons moving between the carbon and the hydrogen. Now these three molecules, methane, oxygen, and hydrogen gas, are all very nonpolar. The molecules, the electrons are going to move back and forth equally between the atoms. Water on the bottom, though, is an example of a polar covalent bond. Oxygen is kind of like the kid that doesn't play well with others. For some reason, the nucleus of oxygen is very electronegative, which simply means that the electrons are really attracted to that oxynucleus. So the oxygen in those chemical bonds with hydrogen is going to attract the electrons more. So those electrons are going to spend more time orbiting the oxygen end and only occasionally going near the hydrogen end. And that means that the oxygen end of the water is going to have a slight minus charge to it because the electrons are there all the time, almost. And the hydrogen end is going to have a slight positive charge to it because the electrons are very rarely at that end of the molecule. Our third type of bond are hydrogen bonds. And hydrogen bonds are different than ionic and covalent on a couple different levels. The first issue that's kind of most obvious is that hydrogen bonds are much weaker than those other two. And so hydrogen bonds are a very weak attraction, not a strong attraction like covalent ionic. The other area where we see a difference is those covalent ionic bonds we just discussed were when one atom is attracted to another. And those two atoms are going to chemically bind together to form a molecule, whether it's an ionic bond forming a molecule of salt or a covalent bond forming the molecule of water. In hydrogen bonds, though, we're going to step up in our scale a little bit, and it's going to be the attraction not of one atom to another, but instead the attraction of one molecule to another. So, for example, hydrogen's bonds form that attract one water molecule to another water molecule. Okay. Now, by definition, our hydrogen bond is when a partial positive or a small positive charge associated with a hydrogen is going to be attracted then to any minus charge. And again, it's all about plus-minus interaction. This is going to be a much weaker bond, though, because it's only a small or partial hydrogen positive attraction. And so let's take a look at an example here. The reason hydrogen bonds are so important to living things is because hydrogen bonds form in water, and obviously as living things we're made up of an awful lot of water. In particular, we mentioned already that water is formed by polar covalent bonds. It's that unequal sharing between oxygen and hydrogens within the water molecule that is going to form that water molecule, but it's also going to give that water molecule those slight charges, a little bit of a minus charge at the oxygen end, slightly positive at the hydrogen. So when we mix a bunch of water molecules together, those water molecules are attracted to each other and are going to bind together through a hydrogen bond. And so hydrogen bonds are the attraction between the water molecules, between that partial positive of a hydrogen in one water attracted to the slightly negative oxygen end of a different water. And so if we take a look at a couple diagrams here, here's our diagram of water. The arrows indicate that the electrons are spending more time at oxygen, so that end is a little bit of a minus charge, the hydrogen a little bit of a plus. So when we mix a whole bunch of waters together, those waters are going to be attracted to each other. The pluses and minuses are going to form these hydrogen bonds. And while one hydrogen by itself is relatively weak, not a particularly strong force, we know we are not going to find one by itself, but instead hydrogen bonds are going to form between all the water molecules. All added together, these millions of hydrogen bonds are going to be a significant force. And as we're talking about water and kind of continuing our chemistry review in Chapter 2, I do want to mention some chemical properties of water, because water has many unique or unusual chemical properties compared to most other substances. Now, we don't think of water as being unusual because so many of the chemicals we deal with are water-based and have water in them. But in reality, compared to most chemicals, water is kind of an odd sort of little chemical, and all of those odd characteristics can trace their way back to the polarity, to that unequal sharing going on between those oxygen and hydrogen atoms. One example of the unique properties is that under normal environmental conditions out there in nature, we find water in all three states of matter: solid, liquid, and gas. And so whether it's ice, it's water, or it's steam, we find those out there under natural conditions. We don't see that with other chemicals. Most other molecules we find in only one of the states of matter. A few maybe in a couple different states, but certainly not all three like we do with water. Along with the states of matter, another unique property of water is that it exhibits what's called cohesion. And cohesion is when two like things are attracted to each other. And in this case, water is cohesive, meaning water is attracted to other water molecules, just like we saw in that hydrogen bond slide just a few moments ago. And this is going to create some interesting properties about water. One is surface tension, and we can see here the little water strider is standing up on top of the stream there. The reason for that is the hydrogen bonds that hold the water together are stronger than the weight of the bug, and so that's why the hydrogen bonds in the water holds up the weight of that bug, is that surface tension. Most chemicals don't exhibit surface tension. Water also has a really high boiling point. If we compare other small molecules, and water is relatively small, oxygen weighs 16, each hydrogen weighs 1, so combined it has a molecular weight or size of about 18. Other small molecules in that range, things like oxygen gas, nitrogen gas, methane, butane, propane, all those chemicals are gases at room temperature, meaning they've already boiled. Not only is water liquid at room temperature, but we have to pump in another 100 degrees Celsius worth of G to get it to boil. Again, very, very unusual. And the reason for that are those hydrogen bonds. Liquid water has enough energy that allows the molecules to move, and the way they move is they move closer together because those hydrogen bonds attract one water to another. And when we convert that water into gas, we have to separate those molecules of water to become less dense. We have to make them farther apart. And to do that, we have to break all those hydrogen bonds, which is why it takes so much energy to convert liquid water into gaseous water. Our last example of cohesion is dealing with some issues concerning density. We said that when we talked about our states of matter, that solids should be most dense and liquids a little bit less dense, which means if I put my solid into a liquid, it should sink because it's heavier, it's more dense. But we know that that's not the case with water, that for water, that's just the opposite. So if we take a look at an example here, I know that if I drop my ice cubes in water, they float. And again, that's not what we would expect. And the reason goes back to these hydrogen bonds. Liquid water, as we can see on the right here, has enough energy in it, those molecules move around, and again, they're going to move close together, so they're very dense. When we take energy out of water to freeze it and turn it into ice, those molecules actually separate just a little bit to form a crystalline structure, which is why ice floats. Again, here we see compared to benzene, most other chemicals, the solid and the liquid, is going to sink to the bottom right away. Another area where water has unusual properties is what's called adhesion. And adhesion is when we have two things that are different and they're attracted to one another. So in this case, water is adhesive, meaning water is attracted to other chemicals. In particular, water is going to be attracted to any chemical that has any kind of electrical charge. And it doesn't matter whether that charge has a plus or a minus charge. Since water has both charges, it's going to be attracted to either charge. And here we can see in this diagram, we know if we take a teaspoon of salt, for example, mix it in a glass of water, the salt dissolves, the salt disappears. Well, the sodium and chlorine are still there, but what happens is all the positive hydrogen ends of the water are going to surround the minus chlorine atoms and pull them away. The negative end of the water, here red in the diagram, are going to surround those sodium positive sodium ions and separate them. And so the chlorine and sodium atoms are still there, but they're surrounded by water. They're dissolved. And we know if we take that teaspoon of salt water and we mix it in, it dissolves. If we take that glass of salt water and set it on the windowsill for a few days, once the water evaporates, those sodium and chlorines will reform once the water is missing, and our salt will reappear. And because water is attracted to so many other chemicals, it's referred to oftentimes as a universal solvent, because anything with a charge is going to dissolve in water. And there are a pair of terms that we use to describe whether things are soluble or not soluble in water, and we'll certainly be using these terms a lot, especially in lab throughout the semester. One of the terms is hydrophilic, and literally translated, hydrophilic translates into water-loving. And so if a chemical is hydrophilic, that's a water-loving chemical, meaning it's a chemical that will mix and will dissolve in water. So certainly salt, from our previous example, is a hydrophilic chemical. It's going to mix very well with water. And the defining feature of hydrophilic chemicals are that they have a chemical charge. Again, anything with a charge is going to mix with water, be very hydrophilic. Our exception to that then of these hydrophilic chemicals would be a chemical that's hydrophobic. And hydrophobic literally translates into water-fearing, and again, this would represent chemicals then that are not going to mix with water, that won't dissolve and become soluble in water. And there aren't many examples of this, but in living organisms, the major examples include things like oils or fats. For example, if I take my salad dressing, my vinegar and oil, the vinegar being mostly water-based, in the fridge, I can see my oil layer and my water layer. If I take that bottle and shake it up real vigorously, I can mix the water and oil up temporarily, but they're going to quickly separate back into their two layers. The reason for that is that the water molecules and the oils get mixed together. Well, the water is not attracted to the oil because it doesn't have any pluses or minuses, but water is still attracted to itself. And so those water molecules rebind through hydrogen bonds, and they'll physically push the oil up and out of the way, and that'll separate things into their two layers. And so hydrophobic chemicals are always going to be chemicals that are very nonpolar, that are neutral, no pluses and minuses, which is going to include mostly chemicals that have lots of equal sharing covalent bonds going on, things like fats and oils and petroleum products, for example. Another important aspect, especially if we're thinking about our chemistry of water here, has to do with acids and bases. And we're all probably familiar with those terms, acids and bases, and we certainly know I certainly wouldn't want to spill a strong acid on my skin. It might burn me. Likewise, strong bases could also be harmful. The reason we include acids and bases together is because both acids and bases are going to affect the plus-minus charges of water. So they're going to impact our ratio of those pluses and minuses. And as we've talked about extensively today, those charges are certainly going to impact the chemistry of the water, that much of chemistry is based on plus-minuses. And so if we throw those plus and minuses out of whack by adding acids or bases into water, that solution's chemistry is going to be very different than if we had just pure or just plain water. Now, acids and bases are slightly different from one another. An acid is any chemical that's going to dissolve in water and it's going to release hydrogen or H plus ions along with a negative ion. So first of all, an acid is hydrophilic. It's going to mix with water, it's going to dissolve, and when it dissolves in water, it's going to break into two pieces, a positive hydrogen ion and then some other negative ion. A base is going to be very similar. It's also going to be a chemical that dissolves in water, so it's going to be hydrophilic, but it's going to break into different pieces when it does. In particular, a base is going to dissolve into a positive ion of some type and also a negative OH minus ion. And an OH minus is called a hydroxyl ion. And so acids and bases are similar. They're both hydrophilic. Acids release hydrogen ions and some negative ion. Bases release the hydroxyl ion and some other positive ion. And as mentioned on our last slide, the names of those ions, H plus is a hydrogen, OH minus is a hydroxyl ion. And whenever I'm thinking about acid-base chemistry or talking about it with students, one question always kind of pops in my mind, and that's, well, why are these two things important? Why do we care about H pluses in acids and OH minuses in bases, but we don't seem to care about the negative ion in the acid or a positive ion in the base? It's just some other sort of afterthought. Okay? And the reason that H plus and OH minus are so important is what happens if I add those two things together. I get H2O, or water. And in fact, hydrogen and hydroxyl ions are the two halves of water. And we know that while if I had a beaker of water, most of that water would be in the form of H2O, our polar covalent bonds holding the water together, that all chemicals are in constant motion. And so as those water molecules bounce around, some of them are going to break in half, and they're going to break into hydrogen and hydroxyl ions. Likewise, as those ions bounce around, they may bounce into each other and reform water. And so water is constantly breaking down and it's reforming. Okay? Now, if I have pure water, I should always have equal amounts of H pluses and OH minuses. For every one positive, I should have one negative, and vice versa. Where acids and bases are important is they're going to change that ratio of the pluses and minuses, such that if I add acids to a solution, now I'm going to have way more H pluses than I do OH minuses. Likewise, if I add a base, I'm going to throw that balance out of whack, but I'm going to have more hydroxyl or more minuses in my solution than I do pluses. So that's the reason acids and bases are important, is they're altering that basic ratio of those hydrogen and hydroxyl ions, and again, in turn, that's certainly going to alter the basic chemistry in that solution of water. And we measure the amount of H pluses and OH minuses in solution with the pH scale. And so the pH scale is going to give us that ratio of how much plus to minus ion do we have in our solution of water. And the pH scale is a fixed scale. It goes from 0 to 14. The low numbers are acids, and so 0 would be the most acidic. That would mean we've got all H pluses in my solution. The high numbers up to 14 are bases, and so something like 14 would be the most basic solution I could have. That would have all OH minuses in my solution. The middle of the scale is 7. That's neutral, which means at pH 7, I've got an equal number of H pluses and OH minuses, and I know the only time I can have that is if I have pure water. Now, the scale happens to be a logarithmic mathematical scale, and we're certainly not going to get into logarithms here in introductory biology, but what that means in terms of a logarithmic scale is that small changes in the pH reflect larger changes in the underlying chemistry. So let's take a look at the pH scale and look at an example of that. So here's a diagram of a typical pH scale out of your book. As we can see in the middle there, pH 7 is neutral. That means my pluses and minuses cancel each other out, and that's pure water. As the numbers get smaller, that means we're moving into the acidic range. The smaller the number, the more H pluses in solution. Things like tomato juice, other citric juices, lemon juice, the gastric juices in your stomach are all things that are examples of acids. If we move at the other end of the scale then, the larger the number, the more OH minuses we have. Things like ammonia, bleach, oven cleaner are very strong bases and certainly can burn you and be harmful to your skin. Now, in terms of the logarithmic aspect of the scale, let's compare water to tomato juice. Water pH 7, tomato juice pH 4. And that sounds like a difference, but not that big a difference. 7 to 4, not a big change. But because the scale is logarithmic, what that means is that for every change I have in the pH of 1, that represents a 10 times or a tenfold in the chemistry. So pH 6 is 10 times more acidic than pH 7. In turn, 5 is 10 times more acidic than 6, 4 10 times more acidic than 5. And so if I move from 7 on the pH scale at pure water all the way up to 4 in tomato juice, that's a change of 10 times 10 times 10, or tomato juice is 1,000 times more acidic than pure water. If we look at a summary or review of some of the important concepts that we've covered today, we know that there are 3 basic types of chemical bonds or attractions between different atoms: ionic, covalent, and hydrogen bonds. Remember, ionic bonds are very polar charges. Covalent bonds involve sharing. Some may be polar or some may be nonpolar. And then hydrogen bonds, much weaker, and they're the attraction between 2 different molecules. Then we certainly talked an awful lot about the chemistry of water. Its polarity determines its special features. Adhesion, the attraction of water to other chemicals, makes it the universal solvent, and we talked about hydrophilic versus hydrophobic. Cohesion, then, the idea that water is attracted to itself, properties like its high boiling point, its water surface tension, and so on. Acids and bases also kind of fall into that category of chemistry of water. We know acids and bases then are going to affect or alter that balance of H pluses to OH minuses in the solution. Acids are low on the pH scale, bases are the higher numbers.